Graphing is never the solution to any problem. Graphing is a tool that leads you to find or appreciate the solution to any problem. And so we have to look on it that way. The goal is not to graph. The goal is to make models and apply them in real world situations, and graphs help us do that. So what we're going to do is a quick reminder of what goes into making a graph, what the tools are. Those are the same tools that we use for calculus for analyzing anything, basically the mean value theorem. And then we're going to do an example, and then I might do another example in a separate video later. But the example I'm going to do is something that comes up in a lot of applications. So the basic of graphing, I said basic, not basics, is this. If f prime is positive, then f is increasing. If f prime is positive, then f is increasing. That's the consequence of the mean value theorem that is most helpful to us, and that's how things go. So when you're looking at graphs and trying to figure out, functions and trying to figure out what the behavior is, there's a pretty simple implication from this. So let me draw a little picture of a point of what's called a local maximum. It's higher than every point nearby, but there might be, you might get this kind of stuff, and then this is the local maximum. And a maximum, people make it really complicated. It's not. You increase up to a maximum, and then you decrease. So the function behavior changes from increasing to decrease. That's the very definition of maximum. And if you go back now to the mean value theorem, increasing function can only happen for a positive derivative, and decreasing function can only happen for a negative derivative. So what you have here is at the input where you have a maximum, you have that f prime changes from being positive to being negative. So you change f from being increasing to decreasing. The derivative changes from being positive to negative. At a minimum, you get just the opposite thing, which is that you go from decreasing to increasing. That's the definition of a minimum. And so you have, if you look on either side of the minimum, f prime changes from being negative to positive. So at a maximum or a minimum, f prime changes sign. Now, if there's a jump in the function, which doesn't happen that much in the applications you're likely to bump into, then that may well still be the case. But anyway, f prime changes sign at a max or a min. It changes sign. Remember, I said sign is the most important thing. And so that's really true. Sign is the most important thing. S-I-G-N, sign is the most important thing. And so that's the good news. The bad news is to tell whether a function changes sign, whether it's the function or the derivative or the second derivative or the seventh derivative, you got to factor it, and you got to factor it correctly. And so that can be a little bit of a stumbling block to applying these ideas in doing things. Another thing very quickly is that if you look at this graph right here, the derivative goes from being positive to negative. The derivative goes from being positive to negative. That's an increase. That means the derivative of the derivative has got to be negative. So, so in this situation over here, we have that f double prime, the derivative of the derivative is negative, because even without knowing the numbers, positive to negative is a decrease. Decreasing only happens if the derivative of the function is decreasing. In this case, the derivative of the derivative is negative. And over here at the minimum, the derivative of f changes from being negative to positive. That's a decrease. Well, that means the derivative of the derivative has to be positive. The derivative is increasing. Negative to positive is an increase. Okay, so let's put this into action with a function that is fairly useful in a lot of applications. And so let me give you the function here. So it's a product. It's x times something. And the second factor is e to something. It's e to a fraction, a negative fraction. The top is x, the bottom is 3. So let's take the derivative of this. Let's take the second derivative. We're going to have to factor, and then we'll see what's going on with the graph. So y prime, you have to use the product rule, is 1 times e to the minus x over 3. That's the f prime g plus g prime f, plus x times, and then this is going to be in parentheses. So in fact, let me show you. I'm going to do the parentheses first. And the derivative of e to the minus x over 3 is minus 1/3 e to the minus x over 3. That's the chain rule, because that's e to the minus x over 3 is a composition. You took x, divided it by minus 3. That's a function, and then you raised e to that power. That's another function. So the chain rule says the derivative of that is the product of the two derivatives. And so so there's the deal. Now this one, this is not factored, it's got a plus. And so let me factor this. So what we have here is a common factor of the exponential, that's e to the minus x over 3. And I'm going to stop right here and say, hey, you know what? E to any power, that's always positive. So the sign of the derivative, the thing that we're most interested in, this has no effect. All right. So that'll make things a lot easier. And then looking at else, what we have is that this is 1 minus x over 3. So the derivative, excuse me, maybe you might want to look at that. The derivative has the same sign as 1 minus x over 3. We don't care about the value of that exponential factor. All we care about is that it's positive. So this is the same sign as 1 minus x over 3. And so, well, when x is really negative, that's positive, and then it changes from being negative. So, let's write that down. We change plus to minus at x equals 3. So we ignore the exponential factor because that doesn't change the sign. Now we just have this linear factor. That's pretty easy, and so we get that right there. Okay, so that's y prime. There's a single place where the derivative is 0, and that's a place where the derivative changes from being positive to being negative. So we're in a good situation. Let's restrict our domain here to x being greater than or equal to 0, because that's what happens in a lot of the applications. Now, if we want to look at y double prime, there's some good algebra tricks that you can do here. What's a good algebra trick? A good algebra trick is one that means you don't have to do much algebra. Okay, so when you're doing that, you have to take the unfactored form, because the factored form is, you got to use the product rule, so forth and on. So I'm going to go back to this thing here. I'm going to take the derivative, and so the first term is going to give me a minus 1/3. Excuse me, I wrote the wrong thing. I'm going to blot it out. E, and then the same exponent we've been using, the fraction x on top, 3 on the bottom. So excuse the blot, but that's the derivative of this, where'd it go, this term here. Now, what we have is we're going to have to use, wait a second, that's the original function. We already did that derivative. That's a good algebra trick. Hey, I already did that. I'm not going to do it again. And so, so what we're going to see here is, first of all, do the parentheses first, and then I'm going to write in the derivative that I just had there, which is e to the same power as before, minus x over 3, times 1 minus x over 3. I already did that derivative. I'm not going to do it again. Come on, get a life. Okay, and then I'm going to do a little bit of neatening this all together, and everything has a e to the minus x over 3 factor. Ooh, we like that because e to whatever power is always positive. And then what we're going to end up with here is, looks like we're going to have a, I've done something different from what I did before, excuse me. I don't think I wrote the derivative correctly. Sorry, bag of macaroni. Gakumono. I'm not going to redo the whole video. This green part is the correct part. The derivative is, oh, I did do it right. Never mind. Ugh. Well, anyway, let's factor this all out, and then you can work out the details for yourself. We're going to have a minus 1/3, and then we'll have a another minus 1/3, and then an x over 9. There's a 1/3 that happened here. So this is e to the minus x over 3 times minus 2/3 plus x over 9. And that only changes sign in one spot because the exponential doesn't change sign. We can ignore that. And so we get that we have a sign change at x equals 6. So that's where the concavity changes. And so let me finish off with just doing the graph here based on what we know, which I'll draw it and then kind of label it. Because a good mathematician, even a good user of mathematics, draws the graph, then puts in the axes. So what I'm going to do here is say, okay, look, there's a maximum when x equals 3. The function is increasing, then decreasing. There's an asymptote because the function is always positive. And then there is a change of concavity. That's called a flex. And that happens when x equals 6. And so the second derivative changes sign from negative to positive, concave down to concave up. And there it is. The name for this function, by the way, is surge, not short for Sergio. It's surge, which is a very apt description of what it does, because you get things that go up and then they slowly fade away. So that's our first good example that has all the tools, first derivative, second derivative, and you worry about the signs, not the values.